So in this problem, we've got a 50,000 kilogram airplane. It's powered by a turbojet engine, and the engine draws in fuel at 2 kilograms a second. It draws in air at 150 kilograms per second, and as the air passes through the compressor, the pressure is increased by a factor of 20. The fuel's got a heating value of 40,000 kilojoules per kilogram, and the question's asking us, based on this information, what is the initial acceleration of the airplane if it starts from rest and full power is immediately applied to the engine. And we're to assume the engine operates on an ideal jet propulsion cycle, and we're given the ambient temperature and pressure of 27 C and 100 kilopascal. And it says assume constant specific heats for air of this value and a heat capacity ratio of 1.4. So in this problem, in a turbojet engine, there's effectively 5 points. There's the inlet to the compressor, there's the exhaust or the exit of the compressor, which enters the burner section, and then the exit of the burner, which enters the turbine, and the exit of the turbine, which enters the nozzle, and then finally, point 5, the exit of the nozzle. So to solve this problem, what we want the acceleration of the airplane, and by Newton's law, we just say the acceleration is equal to the force of the thrust divided by the mass of the airplane. So if we knew the force of the thrust, we know the mass of the airplane, we'd have the problem solved. If we did a momentum balance around the engine, we'd find that the force of the thrust is equal to the mass flow rate of air times the difference in velocity, v5, the velocity exiting the nozzle, minus the velocity entering the front of the engine. And if we make the assumption that the velocity of the air entering the engine is very small compared to the velocity exiting the back of the engine, we can say that v1 is about equal to 0, and the force of thrust is just m dot times the velocity exiting the nozzle. So the thermodynamics we need to work with will allow us to calculate the velocity at v5. We know the mass flow rate of air, it's given to us, and therefore we can find the force and hence the acceleration. The key to solving this problem is to do a series of energy balances and some considerations, some isentropic considerations. So the first thing, one energy balance we could do is an energy balance around the compressor section of this engine. So you've got mass flow of air coming in, mass flow of air leaving, and there's shaft work entering the compressor. And the amount of shaft work entering the compressor, which is used to compress the air from P2 or P1, it's used to compress the air by a factor of 20. So P2 is 20 times bigger than P1. And this shaft work comes from the work output by the turbine. But let's just do an energy balance around this section first. So here's our general energy balance equation. The compressor is adiabatic. There's no significant heat transfer in or out of it. The velocity or the potential energies are about the same. There is no work leaving the compressor, so work out is 0. And the velocities entering and leaving the compressor, although they're different, the differences are really small. So what we're left with is the amount of shaft work entering the compressor plus the rate at which enthalpy is entering the compressor is equal to the rate at which enthalpy is leaving the compressor. And if we use just heat capacity, a constant heat capacity, we can calculate this relationship for the amount of work coming in and the temperature difference, T2 minus T1. And because the amount of work entering the compressor is a positive value, we would expect the temperature at 2 to be greater than the temperature of 1. So shaft work going into the air heats up the air by the time it leaves the compressor. And though it's heated up, we don't know by how much it's heated. But because this is an ideal compressor, it's isentropic, it's adiabatic, and it's reversible, we can use a relationship for an ideal gas. That isentropic compression, because the two entropies are the same, T2 is equal to T1 multiplied by the pressure ratio in this factor for K raised to the K minus 1 over K. And if I plug in values for this, use the ambient temperature, pressure ratio of 20, and this factor of 1.4 for K, I find that at the exit of the compressor, it's not even reached the flames yet, but the pressure or the temperature has been raised from 300 degrees Kelvin up to 700, a little over 700 degrees Kelvin. So we now know something about the state of the air at point 2. Let's turn our attention to the burner, and let's do an energy balance around the burner. So around the burner, there is no shaft work coming into or out of the burner. There is no heat leaving the burner itself, and any differences in kinetic and potential energies are both negligibly small. So what we're left with is the rate at which heat is entering the burner plus the rate at which enthalpy is entering the burner is equal to the rate at which enthalpy leaves the burner. So again, we'd expect, if you look at it for an ideal gas, we say Qin is equal to mCp times the increase in temperature between as the air exits the burner itself. And in that case, if we know Qin, we can calculate T3, the temperature at the exit of the burner, according just by rearranging this algebraically. We know everything. If we know Qin, we can find it. And we do know Qin because Qin is the rate at which the engine's consuming fuel multiplied by the heating value of the fuel. So here is the internal energy, or I guess the chemical energy associated with burning the fuel itself. And if I plug in numbers for this, I've got 2 kilograms a second of fuel multiplied by its heating value. So I come up with Qin, there's 80,000 kilojoules per second of heat entering the burner. And that heat is used to heat the air from point 2 to point 3. So with knowledge of Qin, we now know we can find the temperature at T3. What we come up with is T2 plus 80,000 kilojoules per second divided by the mass flow rate of air times its heat capacity. And we come up with a temperature exiting the burner of 1200, a little over 1200 Kelvin. So we're working our way through this problem. We know the temperature leaving the burner. Let's pay attention now. Let's focus attention on the turbine itself. Let's do an energy balance around that. So here's a simplified form of the general energy balance equation. No work in, no heat in. Differences in kinetic and potential energy are negligibly small. So we've got enthalpy in. Enthalpy entering the turbine is equal to the rate at which shaft work is leaving the turbine plus the rate at which enthalpy is leaving the turbine on the downstream side and entering the nozzle. So again, what we've got in the simplified form, we can say the work at which the rate at which shaft work is leaving the turbine is equal to the mass flow rate of air times its heat capacity times its difference in temperature. So we expect a positive value for the rate at which work is leaving, and in that case, we would expect T3 to be greater than T4. We'll see a temperature drop across the turbine as shaft work is being extracted from it. And another thing to consider is the fact that all of the shaft work leaving the turbine is going into the compressor itself. So with that, we can use a relationship, the rate at which work is leaving the turbine equal the rate at which work is entering the compressor, and plugging in relationships, again, energy balances on both, we'll come up with the differences in temperature based on the mass flow rate of air and the heat capacity. And if we plug in numbers for these, solve for T4, the temperature leaving the turbine at point 4, and I can calculate a value because I know all of the upstream temperatures. I can calculate the temperature leaving the turbine is a little over 800 Kelvin. And this, I might add, is a very important thing to recognize for a jet propulsion cycle. Another important thing to recognize is that the expansion through both the turbine and the nozzle is isentropic. So you've got a perfect turbine and effectively a perfect nozzle. So the expansion between 3 and 4, this isentropic expansion results in shaft work leaving it, and the expansion between 4 and 5 results in the conversion of enthalpy at point 4 into kinetic energy at point 5, which we're really interested in for the design of this engine. So what that says is that the entropy at state 5 is equal to the entropy at state 3, and for an ideal gas we can use this relationship to find the temperature at point 5 as a function of the pressure ratio. So plugging in numbers, we get a final value. The temperature at point 5 of the exhaust is 526 Kelvin. So we see a temperature drop between 3 and 4 because shaft work is being removed, and a temperature drop between 4 and 5 because we're sacrificing or we're generating kinetic energy at the expense of internal energy at point 4. Note that I didn't use, even though the expansion is isentropic between 4 and 5, I didn't use a relationship there because I don't know, we don't know the pressure at point 4. All we know is that the pressure at point 5 is 20 times less than the pressure at point 3. So we do know that pressure ratio, so that allows us, based on the fact that we know the temperature at point 3, to find the temperature or the enthalpy at point 5. So because we know the enthalpies at 4 and 5, we're in a position now, let's do an energy balance around the nozzle. There is no shaft work entering or leaving the nozzle. The nozzle, let's say it's adiabatic, there's no heat entering or leaving. Let's say that the differences in potential energy, again, is 0. And so we know the velocity leaving the nozzle is a very high velocity. And let's say the velocity at point 5 is so much greater than the velocity at point 4 that the velocity at point 4 is essentially 0. So there's very little kinetic energy at point 4 as compared to the kinetic energy at point 5. So here's the simplified form of the energy balance. Note that the mass flow rates of air cancel out of this expression. And we could say the increase in the velocity, again, we're sacrificing or we're converting kinetic energy at the expense of enthalpy. So here I'm solving for V5, the square root of 2 times this difference in enthalpy, or 2 times the heat capacity times the difference in temperature. And if I plug in numbers, I come up with a velocity of close to 800 meters per second. And note the conversion here of 1,000 joules per kilogram. This seems to be a common mistake. Students will forget the fact that this is kilojoules per kilogram Kelvin. We need to convert to joules, and the reason we do that is because a joule per kilogram is the same as meters squared per second squared. We're taking the square root, and we come up with meters per second. So we're almost done with the problem. We do know the force of the thrust is equal to the mass flow rate of air times the velocity at 0.5. And plugging in numbers, 150 kilograms per second times the velocity at 5, we come up with a force of 117 kilonewtons, or a little over 26,000 pounds, which is a pretty typical force for a turbojet engine. So finally we'll find the acceleration, this 117,000 newtons divided by the mass of the airplane, and we come up with an acceleration of a little over 2 meters per second squared. And for airplanes, you often hear the acceleration in terms of g-forces, so I'll take this value and divide by gravity, 9.8, and I come up with an acceleration in the forward direction of 0.24 g's.